we are going on with APMAS pre-recording presentation. Professor Beste Korutlu from TÜBİTAK UME, Turkey. The title of presentation is Plasma Studies in TÜBİTAK National Metrology Institute. Professor Beste, do you hear me?
Yes, I do hear you.
Yes, hello, how are you?
Hello, I'm fine, and you?
Thank you so much. If you are ready, we can start your presentation.
I'm ready.
Okay. And also, I am start the recording.
Thank you. Good morning. My name is Beste Korutlu, and I work in National Metrology Institute, which is under the umbrella of Scientific and Technological Research Council of Turkey. In short, it is called as TÜBİTAK UME, and today I will be presenting you the plasma studies in TÜBİTAK UME. Since we are going through some really difficult times, before going any further, I would like to send my best wishes to all of you listening this presentation. So let's get started. Here is the outline of my talk. I try to keep this presentation as simple as possible so that everyone will get something out of it. This is why I will start with the definition and classification of plasma to the presentation. Then I will continue with the infrastructure and ongoing research in UME Plasma Laboratory and finalize my talk with a conclusion slide. So what is plasma? We all know that matter is made up of atoms, and we are familiar with the three states of matter, the solid, the liquid, and gas. But actually there is a fourth state of matter, the plasma state. So if you follow this arrow, when you give energy to a solid, it becomes liquid. And when you give more energy to a liquid, it becomes gas. So between this phase transition, what happens is that the bonds between the atoms gets weaker in this direction. When we reach finally the gas state, there will be no bonds at all. So the atoms in the gas will be moving freely in every direction. If we give more energy to a gas, what happens is that it gets ionized. This is a natural gas, but when you give energy, it will be ionized so that the atoms will lose their electrons, leaving behind positively charged ions. So this cloud of electrons and positively charged ions is basically what we call as plasma state, ionized gas in the most simplistic terms. So here's the fact for you. Did you know that the 99.999% of the visible matter is in plasma state? So here you see the examples of that plasma state. We classify the plasma into three as equilibrium plasma, quasi-equilibrium plasma, and non-equilibrium plasma. In equilibrium plasma, all the atoms in the gas are ionized. So we will have no natural gas atoms in the equilibrium plasma. And the temperature of electrons will be almost equal to the one of the ions. And they will be, the temperature of this ionized gas will be around 10 to the 6 to 10 to the 8 kelvins. It will be huge. You will find this type of plasma in galaxies, in the sun, or in tokamak. In non-equilibrium plasma, on the other hand, this is a partially ionized gas, so you still will have some neutral atoms in this plasma. The highest temperature will be on electrons, which will be then followed by ions and neutral gas atoms. Okay, and this neutral gas will be having a temperature around 300 to 1000 kelvins. So the examples of non-equilibrium plasma are glowing discharge plasma that you can obtain in a laboratory, the beautiful aurora borealis, the fluorescent lamps, plasma TV, and so on and so forth. Quasi-equilibrium classification is a classification in between the two, where the electron temperature, ion temperature, and neutral gas temperature are almost equal to each other, having at most 20,000 Kelvin in temperature. And this is also a partially ionized gas, and you can find examples of this plasma in lightning, in the core of the huge planets, or in the light of the candle. Okay, let's continue with the non-equilibrium plasma. In UME, we study non-equilibrium plasma. So from now on, when I say plasma, it would mean non-equilibrium plasma. We can divide our studies into two, as plasma in vacuum and plasma in liquid. Here on the right, you see the variety of application of plasma in different branches, like medicine, environment, agriculture, or dentistry. So let me introduce you the infrastructure we have in our laboratory. You see in the middle our vacuum chamber. This vacuum chamber is evacuated with the help of a mechanical pump and a turbomolecular pump up to the pressures of 10 to the minus 17. Then you can feed gas inside this vacuum chamber through these gas flow pipes, and the flow is controlled by mass flow meters. We use argon, nitrogen, oxygen, or helium inside the vacuum chamber. Also inside the vacuum chamber, what we have is we have two conducting plates, anode and cathode. We apply DC voltage across the ends of this conducting plates. Then with this energy, this supply of energy, will ionize the gas inside the vacuum chamber. This is an argon plasma you see on the right. It glows like purplish. And we have also for plasma diagnostics, Langmuir probe and optical emission spectrometer. In the next slide, I will explain this too in more details, but before going to that slide, what I would like to emphasize here is that the whole system here, except the Langmuir probe, is made in Turkey with the help of these companies. Now we are working on a human-made Langmuir probe, so that the whole system will be then made in Turkey. And you can find the details of this study on human-made Langmuir probe in the talk by Dr. Hacı Ahmedov. So let's continue with the plasma diagnostics. As I told you, we have Langmuir probe and optical emission spectrometer. Langmuir probe is just a wire, okay, inserted into the plasma. Since it is inside the plasma, the diagnostic we have will be invasive. And what we do to that wire is we apply a voltage and we read the current across that wire. By the analysis of this IV curve, one can get this plasma parameters, this list of plasma parameters. What is most important for us is the electron energy distribution function. I will come to that one in the next slide, so EEDF. Electron emission spectrometer, on the other hand, reads the emission spectrometer through this window. It is not inserted into the vacuum chamber, so it is a non-invasive diagnostic. We use spectral line ratio analysis in finding plasma parameters. But you should note that in this analysis, Maxwellian distribution is assumed. So there is an assumption in using optical emission spectrometer. The common parameter between the two is the electron temperature, as you can see here and here. We will come to that one also. So the ongoing studies in UME is divided into two, plasma in vacuum and plasma in liquid. Currently, we are mainly working on electron temperature primary standard and UME-made Langmuir probe. For the other two, we are trying to build our infrastructure. Okay, for hot-cathode magnetron reactive sputtering and for water purification by plasma, we are in the stage of building up our infrastructure. So let's continue with the electron temperature primary standard. But before doing that, I have to give you the definition of Kelvin, the SI unit of thermodynamic temperature. You may have heard that since 20th of May 2019, all the base units in the International System of Units is defined in terms of constants, physical and universal constants. Like kilogram is defined as in terms of Planck constant, or ampere is defined in terms of electron charge. Kelvin, the thermodynamic temperature, is now defined by the Boltzmann constant. Here you see the relation between the two. Here, this is the Boltzmann constant, and this is the unit of temperature, Kelvin. This number is obtained by 3 different methods. I will come to that one in the just next slide. The other units, as I told you, are also measured in terms of other physical constants. Okay. But it is not enough to change the definition. Previously, the Kelvin was defined in terms of an artifact, the triple point of water, where the solid, liquid, and gas phase can be observed together. This was an artifact definition. Now we have a universal definition for Kelvin. Okay? But it is not enough to have just a definition for a unit. You have to find a way to realize that unit, meaning that you have to find a way to relate that Boltzmann constant to the thermodynamic temperature unit, Kelvin. So you have to find a link. And fortunately, thanks to the metrology institutes in all around the world, this link can be provided. You see here the acoustic gas thermometry, the electric gas thermometry, and Johnson noise thermometry. This experimental setups looks totally different than each other. But in the end, what they do is they link Kelvin with the Boltzmann constant. I'm not going into the details of these 3 methods, but what's important here is that the studies to link Kelvin to the Boltzmann constant started in 1988. And you see here the blue circles are the measurement by atomic gas thermometry, while the red diamond here is dielectric constant gas thermometry. And the final one is the green cross, which is the Johnson noise thermometry. When you take a weighted mean of these measurements made during the years, you get this average value. This is CODATA 17 value for the Planck constant, obtained by 3 different experiments. Still, they are in good agreement with each other. Okay, so now the electron temperature primary standard, the ongoing work in our laboratory. So what do I mean by a primary standard is that I want to find a way to define the electron temperature in the unit of Kelvin based on the Boltzmann constant. Okay. So on the left, we have the ideal gas. The atoms are moving around freely, unbounded and moving freely. So this is the ideal gas. And we know that the temperature of an ideal gas can be found by this equation. Here on the left is the mean energy, and it is equal to the 3/2 times the Boltzmann constant and the temperature of the atoms here. This is the ideal gas equation. When we go to the plasma state, in addition to the atoms, we have electrons and ions. So, but I told you that by using the Langmuir probe, we can have information on electron energy density function. And if you know the electron energy density function, you can find the average energy. And from there, you can find the relation between the Boltzmann constant and the temperature of the electron. So we find a way to link the Kelvin to the Boltzmann constant by using a vacuum glow discharge plasma together with the Langmuir probe. I'm not going into the details of this very much. Just I would like to show you our primary results. But before showing the primary results, I told you that we also have optical emission spectrometer, and electron temperature can be determined with this one also. But this won't be a primary realization method because, as I told you, there's an assumption in this method. Maxwell-Boltzmann distribution is assumed in this measurement. So this can only be used as a verification of what we get by using a Langmuir probe. And also by using this system, we can calibrate the optical emission spectrometers. In optical emission spectrometers, we use spectral line ratio analysis. In Langmuir probe, we use IV curves. Here you see our primary results in an argon gas at this pressure and at this voltage value. This is the IV curve, and from that IV curve, we obtain the electron temperature as 0.3 electron volt almost. And by using the optical emission spectroscopy in the same pressure and voltage values, we obtain the temperature of electron as 0.3 electron volt again. So then we get the similar results, but again, these are preliminary results. But still, we can, as I told you, we can find a way to realize the electron temperature in terms of Planck constant. Okay, now the future studies are, I will be presenting the future studies. So the first one is hot-cathode magnetron reactive sputtering. Recently, we have submitted a project with the St. Petersburg Electrotechnical University from Russia on hot-cathode magnetron reactive sputtering. So let me explain you a little bit what is going on in here. So here we have an argon plasma, okay? And what happens is that since argon plasma is made up of argon ions and they can move freely, they will be attracted to the negatively charged cathode. Since they are positively charged, they will be attracted to the negatively charged cathode. So if you put a target here, argon ions will heat to the surface of the target and liberate the atoms on the surface of the target. These liberated atoms then will continue to move in the vacuum and will reach a substrate and will coat that substrate, okay? So here, if you put additional gases, reactive gases like oxygen or nitrogen, these target atoms, before coating the surface, may interact with this reactive gas, and there will be a different coating here. And the name magnetron comes from the fact that we have a magnet here. And the purpose of having this magnet is, if you have a magnet like that, the plasma will be confined in close proximity to the target, meaning that the collision rate of the argon ions will be more with the target atoms. So the deposition rate will increase. So magnetron sputtering basically is a deposition technology. But literally what we do is we deposit the surface atom by atom. Okay, what we would like to study is hot-cathode magnetron reactive sputtering. In hot-cathode, the target is heated up to its melting point. In this case, field deposition rate increases even more, and you will have the ability to modify the crystalline structure of the film. What we would like to do in this project is, we would like to construct a generic physical model for hot-cathode magnetron reactive sputtering, and also we would like to develop an optimal control algorithm. So since I don't have much time, I'm not going into the details of this one too much. And let's continue with the final point of my talk, plasma in liquid. Now, I'm really sad to tell you that only 2.5% of the total amount of water on Earth is fresh water. And the death rate, because of limited access to clean water, is 20 people per hour. Yet, we continue to pollute our fresh water by fertilizers, by pesticides, by industrial waste or oil spills, so on and so forth. And the bad news about this is that the current water treatment methods cannot get rid of micropollutants. But if we have plasma, and if we inject plasma in water, we can purify water, even we can treat water even to get rid of these micropollutants. Okay, so plasma injection in water will help us to destroy 99.9% of the virus, bacteria, or microorganisms. Also, in current technologies for water treatment, as you may have heard, chlorine is used. But in plasma, we don't put any additional chemical. So there will be no taste or other odor problem in plasma water purification. Also, this system will be a lot more cheaper and the energy consumption will be less compared to the current water treatment methods. We are now working on a project proposal to submit to Horizon 2020, and now we are searching for partners. Currently, we have partners from Turkey and a partner from Italy. So this is our future project, and we have started to build our infrastructure on this water purification also. And my conclusion for this presentation is that Langmuir probe in vacuum plasma can be used as a primary standard for electron temperature. Also, electron temperature verification can be easily achieved by optical emission spectrometer. In the reverse order, one can also calibrate optical emission spectrometer by using a Langmuir probe in vacuum. Also, Hot-Cathode magnetron reactive sputtering method may lead additional technologies in coating, and plasma in liquid may be the future technology for water treatment. So please stay safe and healthy. Thank you.
Thank you, Professor Beste Korutlu, for this nicely and very interesting presentation. Just now, we can take questions. I want to announce to all our participants. Do you have any question? If you have any question, you can write the chat part, or you can write there. You have a question. We can open your voice, and you can ask your question by yourself. I think there is no question for now. If after our virtual congress, if there's any question, you can send an email to Professor Beste Korutlu. I think that she wants to also to answer your questions. Thank you, Professor, again.
Thank you. Thank you.
You are welcome.